Let's take a look here at example number 1. Assume that oil has spilled from a ruptured tanker, and it's spreading in a circular pattern out on the water. Now, let's suppose that we've calculated that the radius of this big oil spill is increasing, right? So the radius is getting larger, but it's getting larger at a reliably constant rate. It's growing 2 feet every single second. The question that we're going to have here is how fast is the area of the spill actually increasing, right? How quickly or how much extra area maybe are we covering per second? But specifically at the moment in time when the radius of the spill is 60 feet. Okay, so what you can see here is that first off, questions in this section are going to come, of course, in the form of word problems. Now, this isn't a surprise here. You might have even guessed that right from the opening video. But it just means that we have to spend a little more time trying to think and organize our thoughts. Because whenever we're dealing with any sort of word problem, the first task always is to read the question and make sure you understand the scenario. Because if you don't understand the scenario, it's going to be very unlikely that we're going to be able to answer questions regarding it. So one of the things that you'll see that I'm going to do always over on the side here is I'm going to try to imagine this movie of moving pictures. And I'm going to go ahead and actually create 2 pictures to try to help me. I'm going to first sketch out one picture of the oil spill. And since it says it's in a circular pattern, I've drawn a circle here. And in this picture, I'm going to label a bunch of stuff in blue for things that are going to be moving, things that are going to be changing in this movie. So one thing that I can see here right away is that my radius is increasing. So I can go ahead here and I can say, well, the center of my circle isn't moving, but this radius here actually is. And therefore, if I was to ask you, how long is the radius? You couldn't really ask, or you couldn't really answer that question, right? Because if the radius is moving, then how would you tell me how long it is, right? I mean, it's constantly changing. So what we can say then is that what we really know here is how quickly the radius is changing. We know a speed of the radius. We know a derivative for the radius. We know dr dt is 2, or specifically 2 feet per second. Okay, so these are things that are going to then be changing, and here's the associated speed that goes with that. Now, of course, if the radius is changing, that also means that the area of this circle is changing. So I might ask the question, how quickly is the area changing? Well, the answer to this question, I don't really know. I mean, that's really the goal of the whole question. But I can see here that in this moving picture, I can label things that are yet to be kind of determined in some way. That is, like, I don't know the length of the radius, and I can mark that in the picture. Now, if I imagine this circle kind of just endlessly getting larger and larger and larger, I can imagine that at some point, specifically at the point in time when the radius hits 60 feet, I'm going to hit pause on this video. So what I'm going to go down here and do is I'm going to always create a second picture for exactly when I'm going to hit pause. And so I'll mark over here in red the things that have stopped moving. So at this point, if I've stopped the picture when r is the value of 60, then I can start to maybe go ahead and determine some other things about the picture here, right? Say, for example, if r is 60, wouldn't it be possible for me to compute the area of this circle in the stopped picture? Sure, like I know the area here would be pi r squared. And 60 squared would be 3,600, so I know the area here is 3,600 pi. Now, I don't know yet if any of this information is necessarily useful. I'm first just trying to understand the scenario that I've been given. But now that I kind of have a loose idea of what's going on, I can kind of think back to the different steps that I would be working with that we talked about in the last video. One of the first things I want to do is to set up an equation that relates the variables in the given scenario. Then I'll take the derivative of that formula, and then I'll evaluate that formula at the specific moments in time that are relevant. All right, so let's take a look here. I'm going to go ahead and start with step number 1. Step 1. I'm going to try to create an equation that links together the different variables that I'm working with. What you'll notice here is that I really only have a couple variables. I have the radius of a circle and the area of a circle. Those are the only things that seem to be important right now. I know the radius, and I know that I'm interested in an area. Can I come up with any sort of equation that relates an area of a circle with a radius of a circle? Well, there's not too many choices here, but one great choice would be something like, how about the formula for the area of a circle, right? Like area is equal to pi r squared. This relates these two variables together. So step 1 is done. For step number 2, I would just start by saying, okay, I know the area changes over time, and I know the radius changes its length over time, so I'm going to take the derivative of both sides with respect to time. And if I do this, I have to keep in mind that the derivative of a would just be dA dt. That is, I'm imagining a depends on the value of t. In the same way over here, I'm imagining that r depends on the value of t. In order to know exactly how long the radius is, you have to give me a specific time. So now I can go ahead here and I can state this is really pi times stuff with t squared. So I'm going to imagine this as bring the 2 down, lower the power on the stuff by 1, and then take derivative of the stuff. So notice here I haven't plugged in any values yet. I haven't plugged in anything here. Notice I didn't plug in like the value of 60. I didn't plug in the value of 3600 pi because those values were stopped values. And the starting equation always relates to the moving picture. Even my derivative formula right now still relates to the moving picture. It's only in step 3 where I say, okay, now let's imagine that I pause the video. Let's imagine now that I go to my red stopped picture and I say, I want to measure dA dt. What is dA dt in this picture? So notice what this would force me to actually do is to consider what values I can put in place of r and in place of dr dt. Well, if I'm in the stopped picture, the value of r is told to be 60, and we were already told actually back at the beginning that dr dt is 2. It's always 2. So we can go ahead and actually just write that value in as well. Notice that we've replaced all the values over here on the right, and so we can successfully calculate the value of dA dt. And so we can see here that dA dt is going to be 4 times the 60. It's going to be 240 pi. And again, I'm going to leave that as an exact value. So don't round that off. Don't type that into the calculator. Now, the last thing that I'm always going to do here is I'm going to be interested in putting units on my final answer. Now, I could have put units throughout, but sometimes that creates a little bit of extra complexity. And the units, or applying units at the end is actually super, super easy because the units are actually already given to me in this dA dt formula. Notice, or as a format, dA dt indicates that an area is calculated up top and a time is calculated on bottom. First, let's focus on the time. In this question, what have we been measuring time in? If I go back and read it through, see that I've been measuring time in seconds. So I can see here that this is going to be some amount of area per second. Well, here, how would I be measuring area? If my radius is measured in feet, then my area would be measured in feet squared. So boom, I have my units. The area is changing at a speed of 240 pi square feet per second, at least at this moment in time. Notice though, if I would have plugged in or stopped my picture at a different time, maybe when the radius was 100, I would have gotten a different final value here. So depending on where I actually plug in is going to drastically change my answers. Hopefully this gives you a good sense of how we're working these pictures together with these associated steps. The pictures are very important, and I'm always going to recommend that you draw yourself a moving picture and a stopped picture when it comes to doing these problems on your own. And you'll see me kind of work through that again in many of the examples to come.